very good afternoon to all. Don't know what happened exactly with double sessions, but okay, I suppose now we're all here. Also the people who are left in the other session. So I suppose everybody now made it here. Well, let's start, Martin, then. Just to catch up with time lost.
Okay, so if then I can start, and I'll switch on my presentation. Which should be visible by now. So basically, welcome everyone together today. Together with Pablo Ortiz, will present our part of the Biocommon project, which was already today introduced by Oana and Miren before the lunch. So we'll be more talking today about from a purely chemical or polymer chemistry point of view. So also hopefully something which is interesting. Essentially, why are we interested at all in the CO2 separation? Besides, of course, the big environmental impact of the CO2 that we have as the waste gas, we also are pretty much interested in the CO2 as a raw material in the last years, which is also the topic of the workshop, which is also very good to hear that essentially that there are many ideas and possibilities to play with actually such a difficult molecule to play as it's CO2 because of its low reactivity. But as we see, we have few of the available so far ideas, as for example one brought up by Covestro to actually produce foams out of CO2, which brings a big industrial relevance to the whole industry. Of course, membrane separation is not the only method to actually get the CO2 out of the waste gas. Obviously, we have many other techniques, but when we look at the membranes specifically, they can give a big advantage over the other techniques, not only being cheaper if we have a proper technology for that, but also to be strictly speaking more environmentally friendly than, for example, absorption-based methods, where we have to use a lot of nasty chemicals to in a significant quantities to get a good flux of a CO2 in the end. But of course there are some limiting conditions for the membranes if you want to make them, let's say, comparably efficient to the other techniques, and also if we want to make them, as we say, green, we also have to think in a more green way than we used to do that still 10 or 20 years ago. But if we now look on how membrane works, that's a very, very simplified version. If we look on the polymer membranes themselves, we of course think of supramolecular chemistry and obviously of intermolecular interactions between for example, the polymer chain and the CO2 molecule, and the two main types of interaction that we're interested in, and therefore they are built up in our polymer chain, are either based on the dipole-dipole interactions or ionic interactions, essentially. And while the later one are based obviously on the charge transfer. Therefore, if we have the for example, amine-based polymers, we can use this hopping mechanisms of a CO2 ion through the polymer chain on the other side of the membrane. In dipole-dipole interactions, we take advantage of the quadrupole moment of the CO2 molecule, and we incorporate polar groups in the polymer backbone, such as the polyethylene glycol, for example, to have a proper CO2 solubility, which is exactly based on the dipole quadrupole interactions. But of course, membranes on its own can't be only based on one type of such a soft polymer, unless we are talking about cross-linked polyethylene oxide, which is one of commercially available membranes. But this is for sure not a green option because covalently cross-linked polymers are actually pretty much difficult in processability. So therefore we are looking for different options. One of them is of course based on the block copolymer chemistry, where we actually mix two. You would normally think incompatible blocks together. So as here, this is PIBA, so polyether polyamide block copolymer, which is commercialized by our partner Arkema. And essentially, indeed, those blocks, they don't mix together at the molecular scale, so they phase segregate. We have different domains. The polyamide domain, which is semi-crystalline, gives here the material properties, so the mechanical robustness, while the polyether block essentially gives this CO2 solubility in the polymer. And essentially, through this, we actually get a beautiful synergistic effects where we, through mixing two components, we not only gain the properties of both, but we actually get something extra out of it. And this is the main advantage of the block copolymer chemistry. And so as the main objective for the Biocommon, we essentially want to develop bio-based polyether block polyamides, segmented block copolymers, so multi-block copolymers, essentially where we can bring not only bio-based monomers in the structure, but also we want to compete with the properties of the fossil fuel-based polymers, as we obviously want to make it industrially relevant for multiple reasons. And the strategy from the chemistry point of view, at least on the paper, is actually quite straightforward, because what we intend to do is essentially we have a feedstock of bio-based monomers, either for the polyamide or polyether synthesis, and on the first step we prepare those prepolymer blocks, and then later we couple them together, which is in the most easiest fashion is done via condensation chemistry for the polyamide block synthesis, as well as for the block copolymer synthesis. That's a little bit different for the polyether block here, but that will be later discussed by Pablo. So with those polyamides, we of course give them later to our partners, which have a great experience in the fabrication of membranes, which is essentially the final goal of that. So in the end of the day, we want to screen the whole scientific process from scratch. So from the monomer to a final membrane, with possibility in the end of also scaling that up. So actually a really whole scientific process is basically intended to be done. Here we have, as I said, two prototypes based either on the furan derived polyamide block, which is coupled together with the polyethylene glycol in that case, or in the other prototype we use commercially available polyamide 11 from our partner Arkema, which is essentially bio-based, and we couple that with the lignin polyol, which is synthesized by Tecnalia, and that will be a part of presentation of Pablo, who will now take the floor from me. So Pablo, I will now give you the voice.
Yes, thank you. I will try to share presentation. It's the same presentation actually, but can you wait? Enter the screen, share. Can you see my presentation?
Yes.
Yeah, great. So I take it from where Marcin left it. As he said, there are two blocks. One block is the one I will focus on, is the polyol block that is used in these membranes. So usually this is made from polyethylene glycol. That's the typical what is now what we want to substitute, as Marcin said, by a bio-based polyol. And for that, we have thought that the lignin-based polyols are a good alternative. And for that, I have to explain very short overview about lignin. For those of you that don't know it, lignin is a renewable material, the largest source of renewable aromatics, and is present. This is the supportive tissue in plants, and is typically found in wood, but also in other parts of plants. Now, this structure, the structure of lignin is complex, and currently lignin is a byproduct of the pulp and paper industry, where the objective is to extract the cellulose for making the paper or cardboard. Therefore, lignin that can be found, most of the lignin has some characteristics that make it difficult to work with, especially in polymer or in material science. And there are several ways of overcoming these challenges from lignin that are there shown in red. And many of these techniques we have applied or we are applying in these projects. These come down to making lignin that is a big biopolymer, to chop it in smaller pieces so it's easier to mix and to react. Roughly said, again, it's more complex, but just is for today is enough with this for the time that we have. Now, if we go to how the polyols, the polyethylene glycol that is typically used for this membrane, how it's made, we see that it's a simple reaction. It's a anionic ring opening polymerization that basically entails mixing potassium hydroxide typically with this oxidant, with ethylene oxide, and then you get this polyethylene glycol. The same can be for other propylene, polypropylene oxide, polyethylene or polypropylene oxide. That is the equivalent with propylene oxide instead of ethylene oxide. Now, if one wants to have a partially bio-based product from partially bio-based polyol, one can use lignin as an initiator, and then you can do this reaction using lignin as I said, as an initiator, and then graft this change to the lignin. Now, this process requires high temperature and pressures and results in the lignin-based polyol, but also a lot of side products and also importantly, but other of the final products. Now, to overcome these limitations, we have developed a Tecnalia and cationic ring opening polymerization of lignin with different type of oxidants, from ethylene oxide, propylene oxide, butylene oxide, and this process benefits from running at room temperature as compared with a high temperature, also at atmospheric pressure, and it gives product with very low amount of side reactions, more than 95% of the desired product, and also no odor, not bad odor. And I think that an image is worth more than 1,000 words, as it says. And you can see how the liquid, this powder that is on the left, the typical lignin, is converted into a polyol. Now, for this project, we needed typically the polyol, the polyethylene glycol chains that are used in the polymerization are low molecular weight. So we needed to get low molecular weight lignins, and therefore we turn to depolymerize or organosolv type lignin that have a low molecular weight. These are also the most soluble in organic solvents, and we selected two of these lignins after doing a screening of the different lignins, and then we studied the parameters of the reaction, how the oxidant, the concentration, the ratio of the reagents, how it affected the resulting polyols, what molecular weight we got, polydispersity, and OH number, as well as other parameters. Now, we don't know which was the best polyol, and this is part of the research that has to be done. So we synthesized 3 polyols with different characteristics, and we deliver to Marcin and his team, so they can screen them and find the best performing candidate. And based on that, we are going to look back again, do a structure property analysis, and try to improve tuning the conditions of the reaction, try to get a structure that behaves better for the separation. This is us for the project, but we also are working on other application of these lignin-based polyols. And with this, I end up my part, and I give it the floor back to Marcin to explain the polyamide part.
Okay. Thanks, Pablo. Great presentation. So now I'll place back slides from my screen, which should be again visible for you. So essentially, being back at this slide, as you see, we have the two different blocks to be synthesized. We have now described how the new polyether block is made. So now I'll focus on the part of the polyamide block synthesis. So essentially, we aim to have the polyamide block, which is dicarboxyl functionalized in the end, for sake of the polycondensation together with the polyether block at the later stage. So that's very, very important part. But obviously the whole part about polyamide is essentially to find a proper methodology and also proper eventual structure of the block itself to incorporate it into a useful material in the end. And this is what we are doing at Maastricht University. So eventually, as I said, we aim to synthesize furan-derived polyamides. So for the ones that are derived from furan 2,5 dicarboxylic acid, which is derived from sugar. That's why we call it fully bio-based. That's a relatively cheap monomer, which is also industrially interesting to use or to screen such monomer. Simply speaking, we can synthesize a polyamide out of furan dicarboxylic acid derivatives in a few ways. The most, or what we found the easiest and the most promising method so far, is based on the transamidation chemistry. So we actually make use of the aminolysis chemistry, where we use dimethyl ester or diethyl ester as a starting material, and we reacted with the diamine. Here is the C10, so dodecyl 110 dodecane diamine. This is fully based on the polycondensation chemistry, as I said. So also the end groups are pretty much as well as the length of those polymers. So degree of polymerizations, they are fully dependent on the monomer ratio that we use in our feed, and that's all according to the Carruthers equation. And since we aim at low molecular weights and at high acid functionality, we actually use a relatively big excess of the diethyl ester, and essentially we are able to obtain the values of the diacid or diester functionality more or less as we wish to have, but still, of course, we still do have some free amine N groups, as you will see. That's actually quite, of course, a minority, but they are still there, and they will be acting as a chain stopper in our later steps. So we are currently also working at the post modification reactions that will remove this that will remove this amine group from the end of the chain, so it will not act as a chain stopper. But the other thing that we have here, and you're looking on the right hand side at the differential scanning colorimetry thermogram of this polyamide, we see that we have a fully glassy polyamide, which for sake of the block copolymer properties that can be for some reason detrimental, especially for the mechanical properties, because this is also well known that at least partial crystallinity of the hard block is actually important for the mechanical properties of the block copolymer. Therefore, next to those studies on how to essentially remove this free amine group from the end of the chain, we've been also developing the library of those polyamides with the linear comonomers, which are based either on the adipic or sebacic acid derivatives, which are known to basically bring crystallinity into the polyamides. Is basically adipic acid is one of the monomers of nylon 6,6, which is known to be a semicrystalline polyamide, and that's essentially the same for sebacic acid-based polyamides. So in this way, we essentially synthesize a library of those copolyamides, and we were pretty much interested in, of course, not only how we can control the polymerization, the degree of polymerization and our end functionality, which is essentially in most of the cases was satisfying, at least, but also we were interested in where or at which point the crystallinity in this polyamide block will also arrive, which also aids us to pick up the best candidates for the block copolymers. And again, we look at the DSC thermograms of the synthesized sublibrary of the polyamide based on furan and adipic acid derivatives together with the C10 diamine, and we essentially see that the crystalline, so melting transition of those polyamides appears at 60% of the adipic acid content, which essentially means that we have to go at least somewhere close to close to 50-50 feed ratio between the furan and adipic acid monomers, which is obviously not the worst case scenario, because first of all, we can still make the adipic acid bio-based. So this is still pretty much following our measures, but also we can. It will be still. We guess it will be still better for the PIBA processing properties, as we have it only 50-50 and not only, for example, linear polyamide based PIBA, because that's also one of the drawbacks of the current PIBAs based on the linear polyamides is essentially that they suffer from processability. So that's also one of the reasons why we would be interested here in the polyamide, where furan based block will for sure improve solubility of those polyamides. And obviously in the next steps, having the polyamide chemistry done, we of course continue our works at Maastricht University to go towards the block copolymer synthesis. So we are now investigating both prototype B and C chemistry. It's of course a little bit out of the today's time schedule to speak about those results. Also in the view of that they are still in the progress, but hopefully we'll have a chance to speak or to meet again next time. Then also we can share more on how do we proceed towards the final goal of our work package. So with this, I would like to, of course, thank Pablo for sharing with me this presentation and great work of Oana, who was also great coordinator of our project, as well as Katrin, who is the responsible for a lot of work here also at Maastricht University, and you for your attention. So we'll be happy to also answer the questions.
Thank you both. We're running out of schedule a bit, but is there any questions for both speakers, both Martin and Pablo? Well, if there is no question, just one quick look at, I mean, we managed now to dive deep into the polymer science. Probably not all of us are that much familiar with it. Your general view in this project is that you want actually to replace heat-based processes with bio-based block polymers. Is that correct?
Yes, that's one of the goals.
One of the goals, as I understand. So these block polymers that you were talking about, what was the typical application actually that you are at least demonstrating in the project?
Well, essentially, our main goal is essentially to have bio-based membranes for the CO2 separation, and our reference polymers are basically of the same. Or I mean, actually, the PIBA type of polymers, they have basically multiple applications, because they are actually excellent rubbers. But one of them is also CO2 membrane separations. And
how do they compare, for example, to amine-based systems for CO2? So you're doing separation actually. Is it for CO2, just for process industry actually? Are you demonstrating that CO2 separation for process industry?
For example, yes. Even though that's actually none of my specialization, so to say, because we are pretty much doing a polymer chemistry.
Yeah.
So it's all
Okay. Well, just to see the big picture, because as I said, we many of us are not that familiar with different types of such a broad, vast science of polymers. So that's why I was just trying to picture that in the actual process. But okay, is there any other question around? I mean, if you can come up with one, you can always leave it in a message box. So sorry to rush you through. I think we let me. Oh, there is one. Is there? In post-combustion and biogas cleaning. Okay, that clarifies. It's not a question, that's just a comment. All right, okay, let's move on to our next presenter. Adolfo Benito from Carmos Project on CO2 capture. Hi, Adolfo.
Yeah. Are you fine?
Yeah, thanks.
Let me to share my presentation. Okay. Okay. Are you watching it? It's okay?
We can see it, yeah, we can see it.
Okay, perfect. Okay, thank you very much, everyone, to be here, and it's a pleasure to be with all of you here. First of all, I would like to thanks to the Professor Gallucci and, of course, Vesna for all the efforts dedicated to the organizing of this event. Well, I present myself. I am Adolfo Benedito. I am working as leading researcher in IMPLAS. IMPLAS is a plastical technological institute, and we have so broad experience in the last years working on both in CCS and CCU projects because IMPLAS is really is a center, technological center oriented to polymers. Really, our most important interest in the capture of CO2 is the conversion of CO2 in polymers or precursors of high added value chemical building blocks for the plastic industry. But really the main objective of this talk really is to introduce you the current evolution and the state of the Carmos project. Carmos project is a European project that has been funded by the European Commission and that is start in the January of 2018. This means that we are working on this project 3 years ago. Well, really, you can see here the title of the Carmos project. This is tailor-made 3D print structures based on carbon nanotubes and metal organic reinforced materials for efficient CO2 capture. But really, the most important thing that I would like to highlight about the Carmos project is that we are the aim to develop a hybrid CO2 capture system combining a BTCA, this means a vacuum temperature swing absorption unit, with a membrane separation unit. You know that both technologies, solid solvents, to be included in a BTCA unit and membranes has some limitation. This means some strong points and weak points. In this way, developing a hybrid system, we want to have synergetic effect between both and to take the best part of each one technology. Basically, in Carmos project, we have worked really with in the membrane units with commercial membranes, but the greatest scientific and technological innovation lies in the BTCA unit because we are working on very innovative 3D print monoliths that has been composed by solid solvents, and this is a combination of different, a complex combination of different solid solvents, able to make 3D print structures. Another important thing or issue of Carmos project is the regeneration of the CO2 that is captured by this BTCA unit that will be carried out through a thermoelectric heating process that is very well now usually as the Joule effect. As a result of Carmos project, we want to develop and to build 2 different pilot plants in the facilities of our end users with a capacity of up to 350 tons of CO2 capture per year. And really, we are at this moment in the most critical point because we are developing the construction and the building of both pilot plants. Well, the Carbon project is made with a consortium with 15 partners that from 9 different countries, and each of them has different tasks related to their own expertise that range from the production of nanomaterials. We have CO2 association properties such as abalonics, promethium particles, nanoseal. Of course, optimization of the process with partners such as Implast, Sintef, Vito, WAS, 62MIC. The development of the membrane unit that is led by Democritus and SUC, and final end users companies where the pilot demonstration plant will be installed at Petchem, Titan, and Motor Oil, different industries, refineries, and cement plants. Well, very briefly, introducing the problem, everyone knows that the global warming resulting from the emission of greenhouse gases is a major challenge facing the European Union and beyond. Well, that you have important objective aims towards 2030 and 2050. In these roadmaps, the carbon capture and storage CCAs and CCU, as they are central low carbon technologies to achieve all the greenhouse gas emission reduction target for these years. As you know, from all the emissions, CO2 emissions in the world, almost half of them, 45% of the CO2 capture will be from the industrial applications. This means that the rest of the emissions are very diversified by the atmosphere from the urban transport and other sources, but more or less the half of the emissions are from industrial applications. In this scenario that I am telling you, between the 25 and the 40% of the large contribution to the direct industrial CO2 emissions, for example, steel, cement, and chemical sectors, need to be equipped with the CCS systems by 2050 to achieve all this roadmap I am telling you. Well, really, this is a diagram of the whole Carbon project. This is a simplified scheme of the hybrid system that I have commented you. At the top, we can identify the VTCA unit that is composed by 3 different absorption columns. These columns will be fed directly from the first separation membrane with a calculated CO2 concentration estimated around 8–12% of CO2. This flue gas goes out from the first membrane separation unit. As I have the second unit that you can see in the bottom consists in 2 different membrane units that we will feed directly with the post-combustion flue gases. As I have mentioned before, the first membrane will fill the results, or the separate gases from the first membrane will feed the second membrane, and the less concentrated CO2 will feed again the VTCA unit. Really, the idea is finally to join both streams from the VTCA unit and the membrane separation unit to reach a complete single stream around 25% of purity of CO2 after to join both streams. Well, the plans, as I have said, is to build 2 pilot plants demonstrators based on this design, more or less in 2022, with the capacity until 350 tons of CO2 capture per year. Well, this is basically very fast the key objectives of the Carbon project that can be summarized in the build of the industrial scale-up in a full demonstrator. I have mentioned previously, to develop a complete two-stage separation membrane system to couple with the BTCA system. Most important, as I say, the heart of the research on this project is in the BTCA unit, and for development of the BTCA system, we need to work, and we have worked in the development of different innovative dry solvents for composting CO2, based on the combination of different metal organic frameworks, reduced graphene oxides, and carbon nanotubes. Using as binder to have this material polymer, the polyphenylene as binder. Another key objective, important key objective, is to enhance the manufacturing process of each separate material combination. This means we have important leader producers of each of these materials. And well, one objective in this project for this partner has been to improve the production at higher scales of these materials. And finally, the most important issue that we are working in Converge project is to develop packed monolith structures based on 3D printing processes from these solvents, complex solvents. And here in the bottom, we can see a list of different key performance indicators, quantifying the objectives that we are working in Converge project. For example, and summarizing this table, we can say that one of our most important objectives that probably we will reach at the end of the project when we will do the economical study after the validation of the pilot plants will be to reduce the cost capture of the CO2 with this system around 18% of the current cost in these applications. Well, focusing my speech in the BTCA unit, I would like to see that we have worked with the solid solvents, and from this solid solvent has been processed by 3D printing technologies, specifically by FDM, fused deposition management technologies, in print monoliths. Well, the most important thing is to define the requirements that must accomplish these materials to be able to 3D print. These materials must have adequate fluidity, and such a structure must have a high packing density, allowing low pressure drops during the flow of the gases. As I said, the regeneration of the saturated solvents by heating will be done by applying Joule effect and absorption of vacuum temperature BTCA in a very totally efficient way. Well, this is the complex composite materials that we have developed during the development of Converge project. We are trying to reach an intimate interaction between the different components. We have used MOF, we have used carbon nanotubes, we have used reduced graphene oxide. Well, many types of this kind of combination have been made with them, and we summarize all these compounds in 3 different types: 1, 2, or 3 components system. That in our quotidian argot we name inside of partnership of Converge partnership we name pasties. Well, this pasties has been designed based on these 1, 2, or 3 components, and really at this moment, the truly functional from the point of view of CO2 absorption of this has been the 2 and 3 component pasties. Well, really, to reach or to develop these pasties able to make monoliths for CO2 absorption, we have developed different MOFs suitable for CCS processes with different requirements. The first requirement is high volumetric and granulometric CO2 capacity, high CO2 selectivity, high chemical and physical stability, minimal loss of porosity when we are doing multiple heating and cooling cycles, and of course, a low cost. In this way, one of the most interesting MOF material that we have worked in CarbMOF project has been the CPO27, or most very well known as MOF 74. We have worked in the initial moments of CarbMOF project in a small scale reactor system, around 100 grams, and then we have reached until to working in a 5 kilograms of MOF by day pilot scale reactor. About the development of multi-wall carbon nanotubes for CCA's purposes, our partner NanoSil has worked in different oxidation grades of his commercial NC7000 carbon nanotubes and different experimental design based on controlling temperature, oxidation time, air concentration, gas flow rate, carbon nanotube mass has been applied to obtain finally a good material from a processing point of view and of course from CO2 absorption point of view. The same we have done from the reduced graphene oxide for CCAs. Our partner Avalix has worked in the preparation of different reduced graphene oxide with different carbon oxygen ratios until we have reached a good material able to reach the CO2 capture or CO2 absorption performance that we are looking for. Well, it's important, to say that the next step in the preparation of the BTCA unit is the preparation of the pasties. Once we know how works each component separately, we want to make the pasties preparation. This is really a mixing process. And first, we can see in this slide two steps, different steps to obtain these pasties. The first step is a direct pre-mixing of the individual components, while the second step is really intensive mixing in a 3-roll calendar to disperse all the nanomaterials that we are working on. In the project we have worked with a lot. It has been a very long design experiment. We have worked with more than 150. We can say that we have reached around 200 pasties samples obtained with this methodology to finally optimize the best material from CO2 capture point of view and printability to obtain the final 3D print monoliths for the BTCA unit. Of course, the several challenges we are working on to solve during the CarbMOF project. First of these challenges has been that the high absorption values were not penalized printing. The adequate viscosity of printing monoliths has been achieved. We need to avoid the water segregation, given the huge amounts of water that we use on the process to control the viscosity of the final pass to be processes. The control of the shrinkage after the drying of the monolith has been a very, very important issue during the project. And of course, to ensure an homogeneous heating by applying the Joule effect. All these challenges have been very difficult, but the first challenge that we have was that this material has accomplished CO2 absorption values in the range that we are looking for. In the different combinations, the best material that we have found is 2 components or 3 components based always in carbon nanotubes and RGO. But if the material that we have selected for the pilot plant demonstrators has been the combination of multi-wall carbon nanotubes with the polyethylene imine. In the bottom, we can see the isotherms of CO2 absorption, and I can say that we are, with our selected material for the pilot plant demonstrators, we are around 3 millimoles by grams at 1 bar of temperature. Testing more deeply this material, we have found that we have a very high solubility of CO2 over other gases, mainly nitrogen, and this is a material that is stable, has an stable performance over high number of different sorption and desorption cycles. This is very important, taking into account that the regeneration of the material during the BTCA unit work must be as fast as possible to reach the maximum number of cycles without any loss on CO2 absorption properties or performance. Then we can see here next step of the preparation of the BTCA unit, that is the printing of the pasties that we have optimized in the previous work, printing in different monolith structures. Of course, all these pasties has been printed at Victor facilities. I would like to make a special emphasis on the different limitations and challenges that we detected during the first trials. Aspects such as unstable material flow, water segregation, poor material cohesion, irregular shrinkage has been very important issues and challenges that I have said previously that we have been optimizing during the development of all the project. After studying multiple formulations with different binders and dispersing agents, we have reached an adequate and suitable compromise between processability and reasonable loss of the CO2 absorbent properties of the monoliths. Then, of course, we have scaled up the 3D printing to have enough big monoliths to feed the demonstrator pilot plants. The optimization of the scale-up of the monolith production has been done in the WASP facilities, and different printer configurations have been used during with the most promising past formulation, with the objective to manufacture these, as you can see in the photographs in the right side, larger monoliths. Different solutions we have adopted to avoid the shrinkage and the deformation problems during the drying process of these monoliths, mainly because we are talking about very large sizes, and all these problems, all these issues, all these challenges are multiplying during the scale-up of the monoliths. The final objective has been to provide enough quantity and size of monoliths in size quantity for the optimization of the final pilot plants. When we have optimized and built the BTCA system based on this kind of monoliths, where the gas flow is passing through and capturing the CO2, finally all the BTCA system has been assembled at this moment only in a laboratory scale by our partner 60MIC. The Joule effect heating system also has been installed, and now in this moment, just in this month, is currently being optimized to control and homogenize the heating process, avoiding the presence of one of the most nightmares that we have when we heating processes, that is the presence of hot spots. Sorry. Of course, as you can see in the bottom photography, all the sensorization and control system also has been prepared and installed system to control the sorption and desorption process and the cycles, thinking, of course, in the further pilot plant demonstrator scale-up. Then, this is basically the development of the BTCA unit, but in parallel, we have worked in the development of the separation performance of the membrane unit. I have said in the beginning of my speech, the membrane system has been based in commercial membranes, but the most important issue of these membranes is to put in cascade 2 or 3 of these membranes, and to finally to look for the synergetic effects with the BTCA unit. In this way, great advances have been made in these long years of working in Carbon project. Really, currently the separation process has been optimized by placing not more of 2 of this unit in cascade. For the studies that we have done, a dry mixture of 15% of CO2 and 85% of nitrogen was used, similar to that industrial cases contemplated in the pilot plants. avoiding all the contaminants and other toxic material like SOx, NOx, or other toxic subproducts of the cement plants or the many cement plants. Well, the system is currently operating correctly within the expected working ranges as the expected purities of the CO2. Well, we are expecting to join this membrane unit with our BTCA unit that, well, really the development of this BTCA unit is more delayed. One of the reasons, of course, is the pandemic problem that we are suffering, everyone. And we wait in the next month, well, to join both units together and to reach the objectives that we have planned from the beginning of the project. BTA system, as I say, has more or less a few months left to finish its optimization and begin its scaling and integration with the hybrid membrane system. And well, really, thank you very much. This is the current status of the Carmo project. A crucial year awaits for us to achieve the planned objectives and to overcome all the challenges that we have from the beginning until now, of course. And that's the installation and validation of the two demonstrator pilot plants at the facilities of our industrial partners is the most important issue that we have in this year and the next year. Thank you very much for your attention.
Thank you, Adolfo. We're terribly behind the schedule, but there was one question regarding graphene oxide, which from Margaret Dossa, which I think I answered. The question was, Adolfo, are we going to use graphene oxide or functionalized graphene oxide? So I said we are using reduced graphene oxide as well as functionalized one. Is there anything you would like to add on graphene oxide?
In the project, we have used, in the first moment, we use graphene oxide, but really because we need to optimize the reduced graphene oxide. But finally, the objective in Gramos project is use reduced graphene oxide by one reason. Really, in this system, the BTCA unit, the graphene oxide, the purpose is not to capture CO2, is to provide electrical conductivity enough to apply the thermoelectric heating effect, the Joule effect. Well, this effect doesn't work with oxidized graphene, with graphene oxide, only with the reduced graphene oxide. Then another thing that we found during the development of the project is that also the graphene oxide, like the carbon nanotubes, works as a spacer, avoiding the agglomeration of the polyethylene that really is working as a CO2 absorbent. This means that the combination of polyethylene with the reduced graphene oxide or whatever carbon nanotubes, this combination has important effects on the CO2 capture.
Okay, thank you, Adolfo. There was another question from Adriana Diaz, whether the project is conducting life cycle analysis or any energy environmental assessment.
Yes, of course. In the end of the project, we will have, and we are working now on this, we have preliminary results related to the life cycle analysis, the effect of environmental effects of the process in the cement industry, and of course, another partner that we have in the project, but and the effect of our system in both plants. And then we have a techno-economical study to know exactly what the final, because the final objective is to know the final price of the CO2 capture to have a really competitive system for the market. But of course, in parallel to this techno-economical study, we have a complete environmental impact of our BTCA and, well, Carmov unit, Carmov pilot plants in the cement plant and, well, in another plant in the, sorry, I forgot, sorry.
All right. Adolfo, are you still there? Yeah, maybe we lost.
Yes, I am
Oh,
here.
yeah. All right. Okay. So that was, yeah. Okay. Let's move to the next. Thank you, Adolfo. Sorry to cut you off, but we have to move to the next presenter. It's Richard Hain, an introduction to Cosmos projects.
Thank you very much. Let me manage to show my screen here. Am I showing it, or am I being technically incompetent?
We can't see it.
Okay. So I'm being technically incompetent, huh?
No, you know that arrow is next to the mic?
Yeah, I did that.
All right. Okay. Well, sometimes takes a couple of seconds to show up. I don't know if that's the case now. Or you should choose offered windows.
There we go. Sorry, it works a little different than the normal Teams.
Exactly.
Okay. I hope everything's okay now.
Yes, ready to go.
Very good. Okay. What I will be doing now is giving you all a short introduction to the Cosmos project. Hopefully we can catch up a little bit on the time. I'll be just giving you an overview, an idea of what the project is all about. There will not be a lot of results contained in this presentation. I will leave the description of the results to those chemists who are actually doing the work. So the Cosmos project is a 4-year project, which is not even 2 years old yet. The coordinator is Professor Unni Olsby from the University of Oslo. We have 4 industry partners: Haldor Topsoe, Linde, Tata Steel, and Tüpraş. 4 RTO partners, and then our foreign partners, which was required by the call text, is the Institute for Coal Chemistry in China and KAUST in Saudi Arabia. This is a figure that we like to use to describe what the Cosmos project is in a nutshell. In a very simple manner, we want to have a circular economy approach to solving energy and chemistry or chemical challenges. So what we want to do is we want to take CO2 from the industry, and then we want to do a process intensification where we combine 2 reactions, the hydrogenation of CO2 to methanol, and then the methanol to hydrocarbons in a single reactor with a bifunctional catalyst. And then our aim is to produce C3 products, propane, which can be used as a fuel, or propene, which is a chemical and is the monomer, for example, to make polypropylene. We have 5 operative work packages, if you will, 7 in total, but I won't discuss the ethics and the management. The primary work package and the main focus of the project up to now has been the optimization of the catalysts and the process conditions. This work package is led by the University of Oslo and incorporates the majority of the academic partners. Haldor Topsoe will be upscaling these catalysts for use in the pilot plant. Work package 2 has to do with the process design and optimization. For this, we are leaning very much on the expertise of Linde to design a lean process for the conversion. Work package 3 is the demonstration, which will be done at a TRO 5. This is led by our partner in Turkey, Tüpraş. Work package 4 has to do with the LCA-TEA and the social aspects. Hopefully you all attended the presentation by Guillermo Garcia from the University of Sheffield, which provided a little bit of background on this earlier this afternoon. And then work package 5 has to do with the communication, dissemination, and outreach. Project overview. One of the key points of this project is that we have 2 different industrial sectors on board. We have the steel sector represented by Tata Steel, and we have the refining sector represented by Tüpraş. And so we have 2 different mixes of CO2 emissions that we can study. So what we want to do is we want to take these CO2 emissions and develop new catalyst systems that will increase our conversion of CO2 and hydrogen to these C3 molecules that we wanted. We're looking to have high selectivity, and we want to be able to work at lower temperatures and pressures than, for example, normally used in the methanol synthesis. As part of this, we want to have a single reactor in design, so we want to integrate everything into one reactor with a moderate temperature and pressure, and be able to have flexibility in the amount of hydrogen that we actually use in the chemistry. Then this will all be scaled up to a TRL5. As I mentioned, the pilot plant will be located at Tupraş in Turkey, where we aim to have continuous operation for 7 days, show this versatility in the CO2 feedstocks, and also determine if we actually have this product variability with the amount of hydrogen that we add to the reactor. As I mentioned, we want to make propane and propene C3 products. Propane is, as I mentioned, a fuel, and propene can be used as a monomer or a starting point for a variety of other chemicals. To support this, the scientific work, we have the work on the social sciences and humanities, where we're looking at the impact of this on the CO2 producing industries, the acceptance of this technology and its perception, and of course, as all European projects, we have to be able to communicate and disseminate our work. So the product objectives, we want to have a energy efficient, economically viable, and environmentally friendly process. We want to develop, optimize, and upscale this combined catalyst, which for the two functions that I've indicated, the hydrogenation of CO2 and the methanol to hydrocarbons. We want to have this combined in an optimal system. We want to have the optimal process conditions, so we want to be able to control the heat and pressure. We want a minimal separation at the end, from the outlet of the reactor. And then we want to integrate all of this into a relevant environment. So our primary innovation is these tailor-made bifunctional catalysts. And then our second innovation is this idea about having a single reactor and an optimized global process design. The impact of this is very important with respect to the defossilization of the chemical sector. So according to Decema's landmark study in 2017, if you are able to do this chemistry from CO2 and hydrogen through methanol to propene, then the decrease in your CO2 emissions are estimated to be around 2 tons of CO2 for every ton of C3 product. And our industrial partners expect that we'll be able to convert 0.4 megatons of CO2 by 2030 and 2.2 megatons of CO2 by 2034. And as I indicated, we want to have flexible solutions that meet the local requirements in the different industries that where you could implement this technology. And one of the key aspects of this is the availability of hydrogen. And as been emphasized by a number of times, this hydrogen has to come from renewable energies, which have no appreciable carbon footprint. Otherwise, you will not be able to achieve these these decreases in CO2 emissions, as I indicated a minute ago. So scenario one is, for example, a place which could be relatively remote, where you have an abundant amount of renewable energy to make your hydrogen, and you have CO2, but something that's relatively remotely located, so that you can then transform your CO2 into propane, which you can then is easily transportable. It's transportable today without any issues, and it's an energy vector which can be used for heating, cooking, and transport. For example, one potential location for scenario one would be the ceramic industry in Italy, which I have recently learned is relatively remotely located without a lot of other industries around that could perhaps utilize the CO2 in a different manner. Scenario number two is a more industrialized area where you have, I refer to it as limited renewable energy, or you could say there's a high demand for the renewable energy and there's a high demand for the hydrogen, and where you can then say use less hydrogen and make propane and then conveniently transfer that to a nearby chemical plant. Now, the chemical rationale for this has to do with thermodynamics, and in this case, we want to make sure that Le Chatelier is our friend. So that the point is that all CO2 chemistry has thermodynamic limitations because it lies in this well, and then you have to put in energy in most cases to bring it out of this well to make something that is useful. So the two figures that I am showing here on the slide show you on the left show you the amount of the equilibrium limit of methanol if you just are doing that one first step, CO2 and hydrogen to methanol. As you see on the right, if you combine that methanol production with the methanol to hydrocarbon reaction, the amount of methanol that you can make and your CO2 conversion increases dramatically. So that in theory, as a basis for this project, we expect that this combination of reactions where you take the equilibrium limited product methanol and immediately convert it into a different product will help us push from reactants toward products. And then thermodynamics is also in favor with respect to our temperature and pressure window, so that there is a range of temperatures, say from 130 to 300 degrees Celsius, where the production of these C3 products is actually thermodynamically allowed. The scientific partners in the project have been very proficient in writing up their data. So I'm showing you here a list of the publications that have just thus far come out of the project. Uni Olsby, the coordinator and the leader of Work Package 1, will be discussing a lot of this chemistry and catalyst, on the catalyst development work tomorrow around 12:30, if I remember correctly. So the Cosmos project aims to combine these two catalytic processes into a single catalyst and process for the conversion of CO2 into these C3 hydrocarbons. We want to exploit Le Chatelier's principle to push these equilibrium limited CO2 conversions to higher, much more industrially relevant levels. The conversion of the CO2 to these C3 products is, from a theoretical basis, thermodynamically accessible. And we want to optimize these process conditions to minimize the recycle and the energy requirements. And as I stated, the vision is to be able to tune this chemistry so that we can make propane or propene, depending on the amount of CO2, the amount of hydrogen, and the other industrial infrastructure in which the CO2 is located. Thank you very much.
Thanks, Richard. Let me see, there's a question coming in. Thermodynamics is clear and will come down to kinetics of both conversion processes. Can you say something about the kinetics of the methanol process compared to that of C3 production? For example, which is the rate limiting step? This comes from Paul Cobden.
Paul, I think you should attend Uni's presentation tomorrow, and she will give you a much better and much more thorough answer to your question than I possibly could.
Yeah. I also had a question, but actually I thought let's hang on till tomorrow and find out about the bifunctional catalyst that you've been using. Thank you, says Paul. And yeah, thank you, Richard. We have to move on to our last presenter. Dr. Petrescu, Converge technology for efficiency methanol production with negative CO2 emissions.
Hello. Good afternoon, everybody. Can you hear me?
Yes, we can.
Okay, great. I will try to share my presentation now, and please let me know if you are able to see it. Not yet?
No, not yet.
Now?
Not really, no, I'm afraid.
Okay, I will try to do something else in this case, because I didn't share the screen, only the presentation. So let me try in this case to share the screen. And let's see if I can solve the problem in this way. So are you able to see now?
Yes, that's great.
Okay, great. Thank you. Thank you for letting me know. So good afternoon, everybody. First of all, let me introduce myself. My name is Letiția Petrescu. I am from Babeș-Bolyai University from Cluj-Napoca, Romania. And in this workshop, I am one of the people representing Converge project. In the next 20 minutes, I would like to talk about Converge technology for for efficient methanol production, energy, and environmental analysis. A few words about the Converge project. So Converge project is concentrated on the green methanol for biofuel production using waste feedstock as a raw material. We are going to focus on 4 different types of raw materials from 4 different regions. These are going to be characterized and used in process modeling and simulation tasks. Also, the characterization of the waste feedstock will be important input for the environmental assessment, which is based on the LCA methodology. Using process modeling and simulation tools, the optimum economic layout for the Converge technology will be identified. Another important task of the project is represented by the environmental assessment, as I mentioned before, and LCA will compare the environmental impact of Converge to other green methanol production processes. The social impact will be also evaluated within this project, and the project deals also with the BTX valorization as well as CO2 valorization. So Converge process use the concept of process intensification in order to convert biomass to biomethanol and furthermore to biodiesel. And it is based on the combination of 5 innovative technologies, which are represented by the catalytic cracking of tars, by the recovery of refinery products, including aromatics, the sorption enhancer reforming, the electrochemical hydrogen compressor, and the methanol synthesis using a membrane reactor. The advantages offered by each process steps are summarized in the present table. For instance, the catalytic cracking of tars remove the separation of high molecular weight tars from downstream processes. If we are talking about the sorption enhancer reforming, this will lower the temperature at which reforming is performed and produce a CO2 stream that only partially needs to be compressed for methanol production. The electrochemical hydrogen compressor is an interesting technology that eliminates the mechanical compression cost for hydrogen compression, and the final step will be the methanol synthesis using a membrane reactor. Talking about advantages from technical, economic, and environmental point of view, I would like to stress a little bit the reduction by 30% of the energy losses related to biodiesel production, and this will lead to an increase of about 12% in the production. In the syngas treatment, there is an increase up to 5% in the carbon to hydrogen purity, which lead to an increase of the overall carbon usage. In the sorption enhancer reforming, we expect a reduction in the hydrogen production and CO2 separation from 2 megajoules per kilogram of CO2 down to 1.2 megajoule per kilogram of CO2. And in the last step, in the membrane methanol synthesis, a single pass conversion higher than 33%. From the economic standpoint, it is expected a reduction with 50% of capex for the overall process, thanks to the equipment reduction and the reduction of about 10% of OPEX as a consequence of a more efficient production. From the environmental point of view, the main advantage will be the reduction of CO2 emission by 0.2 kilogram of CO2 per kilogram of methanol. My other 2 colleagues from the project will present the results obtained in other 2 work packages, and I would like to stress a little bit the objectives and some results of work package 5, which is entitled Socio-Techno-Economic Assessment. The objective of this work package was to define the preliminary layout of the Converge process, and also to define the base case to whom the Converge technology will be compared. In order to reach this objective, the steps we have performed are the identification of the possible raw materials for base case and Converge case, the identification of the main blocks for the 2 processes, the identification of the best operating conditions of various subunits, and the construction of the process flow diagram. The tools which are used are process modeling and simulation tools such as Aspen Plus Process Simulator, and the models are validated using experimental data from other project partners. The results obtained in this work package will be the detailed mass and heat balances for the base case and the Converge case, and also the technical key performance indicators and the plant economics. So the objective of this work package are focused on the sustainability, which is based on the technical, economic, environmental, and social impact evaluation. Now let's move a little bit to the technical stuff. So the base case to which Converge technology will be compared is represented in the present slide. This refers to the methanol production through biomass indirect gasification, followed by the syngas cleaning and compression. After that, the reforming for methane conversion to syngas. After that, we have the step of acid gas removal, another step for syngas compression, and the last step is represented by the methanol synthesis and the methanol purification. For the Converge case, the process flow diagram is reported in the present slide. So it contains the following important subunits: the biomass dryer, which is followed by Milena gasifier, where the biomass is converted into syngas using steam. Syngas obtained from the biomass gasification is sent to the syngas cleaning and conditioning step. Beside the syngas, in the indirect gasification, we have also the generation of TARs and BTX. The third block is represented by the catalytic cracking of TARs. The catalytic reaction converts the long-chain condensable hydrocarbons, and the BTX scrubber removes the benzene, the toluene, and xylene, and these are considered to be valuable byproducts of the process. Moving one step forward, we arrive at the sorption enhanced reformer, which involves the use of high temperature calcium oxide based solid CO2 sorbents together with a reforming catalyst. Methane reforming, water gas shift, and CO2 capture occur simultaneously in this step. CO2 removal shifts the chemical equilibrium towards a higher hydrogen yield. Two streams are generated here, an almost pure stream that after compression is sent to the methanol synthesis, and another stream which contain mainly hydrogen and some traces of water, nitrogen, carbon dioxide, and carbon monoxide. And this is sent to the compressor in the electrochemical hydrogen compressor. This is a nice technology where the pressurized pure hydrogen stream is obtained for the methanol synthesis. The last step is represented by the methanol synthesis. As I mentioned before, it occurs in a membrane reactor. The present slide summarizes the similarities and the differences between the two cases investigated. As you can notice, the biomass drying section is the same as well as the syngas production. Both of them are based on the indirect gasification using Milena technology. The differences arise in the tar removal. For the base case, we have the oil scrubbing using Olga technology, and this was selected because of low consumption and integration with the gasification unit. In the Converge process, we have the catalytic tar cracking, which is combined with the BTX scrubber in order to extract the additional high-value production product and to recover the methane and to adjust the syngas composition. The base case use a conventional tubular reforming followed by an acid gas removal, which is based on and on-gas liquid adsorption using MDA. And in the Converge case, the water scrubbing is also present, and the CO2 removal is performed using the sorption-enhanced reforming technology. The methanol synthesis step is also different in two cases. In the base case, we have the boiling water reactors, while in the Converge technology, we have the membrane reactor. The membrane reactor has improved the yield with respect to the boiling water reactor. The separation and purification steps are very similar. Three possible biomass types were characterized, and they are going to be used in process modeling and simulation tasks. The biomass selection was based on the availability of the biomass. And these three possible examples of biomass are forest residue, cereal straw, and residual lignin. Up to this moment, the attention was focused on the forest residue biomass, and this biomass was considered in the base case, in the Converge case, for technical, economic, and environmental evaluation. Talking about the technical results, coal gas efficiency for the most important subunits such as Milena or cleaning or reforming or methanol synthesis step were considered. The coal gas efficiency was calculated as a heating value of product gas divided by the heating value of feedstock. I would like to mention that for Converge technology, several designs have been investigated using process modeling and simulation tools, and one of the preliminary design is reported here under the name Converge, and the best design obtained up to this moment is also reported under the name Converge Optimized. The differences between the Converge and Converge optimized design is the following. So in order to increase the efficiency, we have considered in the Converge optimized design that the sorption enhanced reforming is operated adiabatically, and also the off gas from the electrochemical hydrogen compression are recycled to the sorption enhanced reforming in order to increase the methane portion. So the off gas methanol section are minimized, recycled as much as possible to the synthesis reactor, and in this case, the methanol production will increase. As you notice in table 3, the CO2 separation and the methanol purification have high efficiency. Lower efficiency in the cleaning section is due to the combustion in the catalytic cracking of tar process. And the performance of the sorption enhanced reforming is about 88% in the Converge design. This is the case if all the CO2 have been removed because of the excess of carbonation heat with respect to the reforming heat demand. If we perform the thermal integration, the coal gas efficiency will increase up to 94%. As already mentioned, the methanol efficiency is increased in the membrane reactor. Even if the sorption has reforming has a lower efficiency, it performs reforming and CO2 separation in a single step. So this is the good point of this technology. This base case was also investigated from apart from the technical point of view, where we have considered 3 plant capacities, more exactly 10, 100, and 300 megawatts. As you can notice, the methanol production and also the quantity of CO2 which is separated is increasing linearly, passing from one scale to another. Talking about cost, here we can notice that there is no more linearity when passing from one scale to a higher scale, and this is mainly due to the economy of scale. The levelized cost of fuel is decreasing when the plant capacity is increasing, and for a capacity of 300 megawatts, the levelized cost of fuel starts to be competitive with the methanol price, which is obtained in the traditional technologies. These are the economic results only for the base case. The economic for the Converge technology is an under development task. Another task within this work package deals with the environmental evaluation using the LCA methodology. LCA was defined by the ISO standards and deals with the evaluation of inputs, outputs, and potential environmental impact of the product system during the product or process lifetime. And it contains four phases, more exactly the goal and the scope definition, the life cycle inventory, the life cycle assessment, and the interpretation of the results. Talking about the goal and the scope definition, so the goal of the present study is to evaluate and compare the environmental burden of biomethanol production process in the Converge technology with other technologies for biomethanol production. The scope is focused on the definition of the boundary condition of the functional unit and of the plant lifetime. The functional unit was chosen to be 1 ton of methanol, the plant lifetime 20 years, and the plant location for the forest residue is Sweden. Talking about the boundary condition, I can say that the boundary conditions are drawn around the main processes consisting on the biomass drying, syngas production and cleaning, and methanol synthesis. And beside the main processes, the system boundaries should also include additional processes which are represented by the upstream processes such as biomass supply chain, the catalyst production, the solvent for the acid gas removal for the base case, the sorbent, or the membranes production. Downstream processes will be focused on the solvent degradation, on the sorbent disposal, and the catalyst disposal. The next step will be represented by the quantification of the inputs and the output, which is under the umbrella of life cycle inventory. Based on the life cycle inventory, various environmental impact indicators can be calculated and compared. The recipe life cycle assessment method is going to be used within this project, and the environmental impact indicators are listed on the right-hand side of the slide. Global warming potential, freshwater eutrophication potential, ozone depletion potential, and so on. So these are some preliminary environmental results where we have summarized the results in the base case and in the Converge case. As you can notice for this table, there are some environmental impact indicators such as ozone depletion potential, freshwater eutrophication potential, human toxicity potential, terrestrial ecotoxicity potential, which perform better in the Converge case. But this is the preliminary Converge layout, not the optimized one. Our hope is that once we have finalized the heat and mass balances for the optimized Converge concept to have lower environmental impact in all the environmental impact indicators, or in the major part of them. Talking about global warming potential, here you can notice that in the Converge case we have a higher value for the global warming potential, but we don't have to forget that this will be considered as a negative emission because the raw material which is used for biomethanol production is biomass, and with one of the project partners, which is responsible of the biomass supply chain. We have identified the quantity of CO2 which is requested for the biomass growth, and this is around 5.2 tons of CO2 per ton of methanol. Coming to the conclusion, I can say that different types of biomass are considered or will be considered in the near future in the Converge project. The attention was focused up to this moment on the forest residue biomass. The cereal straw and the residual lignin will be considered in future evaluation. The calculation of the technical key performance indicators for the Converge concept have been performed. The economic analysis is it's an ongoing task, and environmental impact was evaluated only for the main process, I mean for the base case and for the Converge concept, but upstream and downstream processes should be included in the analysis. That's all. Thank you for your attention. Hello. Can you still hear me? Hello. Can you hear me or not? Hello.
Hello. Can you hear me, Leticia?
Yes, I can hear you, but I think we we lost each other here.
Yeah, yes. I got cut off for some reason. I just sent an email about it to Alessandro. Okay, I'm back, fortunately. So I missed the very end of your talk. I think I saw one question in the chat box in the moment when I was cut off.
Regarding the membrane, maybe?
Wait a second. No, it's not now in my chat box any longer.
Even me, I can see only, so I can see the chat, but nobody in, so it's quite strange what's happening here. It was a question about the membrane.
Yes, if we recover, I think the best is just to send it per email. But anyways, I was planning to ask you just at the very end, now that our session is anyway was running lengthy. I want to ask the majority of total energy consumption that you said, actually reduction, will come from this sorption enhanced reforming unit and another one. Is that correct?
Yes.
Okay, what was the other? Sorry, just out of curiosity, because I did not manage to catch everything. What was the other unit? It was EH. Something was reduced from 16 to 12, I think. Yeah, 60 to 12 megajoules to kilogram per.
The methanol synthesis?
No, I think it was referring to hydrogen. But okay, I mean, just the general lines are that these two units are contributing. I mean, what's the major energy reduction coming from? And I understood it's from SCR and another unit. Is that correct?
Hello, can you hear me?
Yeah, actually, I did not hear you.
I lost you this time. So
yeah. Well, okay. If you want, we can just send you those questions when we catch them from the chat boxes. One previous one. While you were talking, there was one more question. Oh, yeah, I found it actually. It's from regarding the membrane. What type of membrane do you usually use?
So our partner, which is TNO, it's testing various types of membranes now, and they are focused on the best 3 membranes, but I didn't include them in the analysis, in the LCA analysis up to this moment. But I think Maria from TNO is going to have a presentation on this.
Okay, all right. Okay, we should actually all move on if there is at all poster session waiting for us afterwards. A coffee break. But this was the longest, probably lengthiest session ever, but nonetheless, it was an interesting one. So yeah, thank you all for listening and staying with us. So yeah, let's move on and see if the poster session is still running at all.
Thank you.
Okay, thank you all very much. Bye-bye for now.
Bye.